I'm in Chem Lab 1 right now.
Okay, then I'll tell you. I can show you.
Tuesday, it's
I really don't want to. I can't.
Okay, what's the number for Kevin?
Or which one? 2 or 1?
Oh wait, that's 1. 30 to 5.
It would be on the 1. One of you.
Oh yeah, I got it the week.
Yeah.
It was a really difficult study.
0.
First one is actually tried. Tracy's excluding like this.
That's a good question.
For example,
This are here.
physics 41.26. I agree.
Sorry, wait a minute.
Making chemistry already, bro.
Oh, but that's it. Got 2 1 2 5. I think. Actually. You can say that.
That's true. That is versus.
Huh?
But actually, it's gone.
Bro, I think wait, they get rid of. I think they didn't get rid of it. Yeah, it's very bad. It's not.
How am I supposed to do my labs if it gets taken instantaneously? Go to
Yeah, it's near interaction.
Is this what's gonna happen at all 4 of my years? Well, these are the ones that fill up facts. The later years.
Yeah, no, because these are introductions.
Like everybody's taking it for these. I'm not supposed to take it, I'm not.
Am I going to do my senior year? You could, so you're going to be, you're 16 here.
If you're going to Chem Lab, the senior for like this is his 5th year, this he didn't do his chemistry. And after this one class, then he graduated. It's
Why are you doing it for the software?
I guess.
A whole year of fault is a semester.
Go to
You can put yourself on the wait list.
he's never used to be
Theory.
But you're gonna, yeah, that'll show you all the cheapness later, right? Me?
All
You said Chem 111? Yeah.
I love the person who valued valued
Okay, any questions before we get started? Number 4 is actually the grade distribution of Newton 2. So on the top is actually the midterm 1 grade, bottom is actually midterm 2. And average is actually basically the same, 55. Okay, so remember what I said in the very beginning that in the past, what observed is that typically in midterm 2, the class will perform much worse than the midterm 1, right? Which typically will drop the grade between 5 to 10 points. Okay, but you guys actually perform pretty similarly, meaning that you guys actually beat the trajectories that people expect that's going to happen. Okay, so great job on that. And I believe our section actually do much better than other sections. Other sections you'll see is very clear characteristic for the midterm too. Okay, so I hope that you can see that the way I tell you how to prepare exam, it is effective. Okay, so keep doing that. There's actually not many lectures left, right? So we probably have 3 more weeks, and that's it for this semester. So you are almost done. So hang on to it, okay? And I will actually start to grade the bonus point this weekend, and you should actually see the updates next week. Okay. So, any questions about? Okay, so if not, then what we're going to do today is actually try to finish this chapter 17, part 1. Okay. So we're still going to go through a few readouts, maybe for one readout question before I head into the things that we want to learn today. So the main focus of today will be tell you how to comprehend the things called the electrochemical step. Okay, and then from your homework and quiz, the term you're going to see a lot is these two terms: galvanic cell or vortex cell. Okay, so we'll actually go through every single needed information for this electrochemical cell. Okay, so let's actually the main focus today. Okay, but before I actually go back to layer, I want to actually practice one more questions with you. Okay, so to really make sure you can handle all this redox reaction properly. Okay, this will be actually a big part of your midterm 3. Okay, so I hope right now everybody knows how to assign your oxidation number if I give you a chemical formula, right? That's actually something that you need to be really good. Okay, so you can identify the oxidation number quickly, right? After you can do that, then we do this 4-step process. Okay, first step is actually to identify who is actually your LoRa, who is your G-rock. Okay, and after that, we'll try to actually balance the atoms based on the solution that you have. If you have an acidic solution, if you're missing a H, you use H plus. If you're missing a O, then you use H2O. If you have a basic solution, you're missing an H, you use H2O. If you're missing O, then you use OH minus, 2OH minus. Okay. So one thing that's actually tricky is that if the compound contains OH, okay, so what we do is actually you ignore OH first. Okay. The compound name option you have, and then you know what's the expected amount of OH minus on the other side. Okay. And then add in the missing part. Okay, so that's actually the only exception that we have for this root. Okay. And after that, then after you balance in your atom, then you start to look for the orbital charges. Then you try to use electrons to balance the charge. Okay. Once you finish that, then you compare your LoRa and G-rock. The electron produced by your LoRa equals the electron accepted by your G-rock. If not accepted, then you actually find these common factors. Okay, so that the electron will be equal between the two equations. Once you have that, then you just add up your equations to get the final redox equation. Then actually looking for the coefficient that you need. Okay, so that's actually basic logic for these 4 steps. Okay, so let's do some practice for that. Okay, question number 6. Balance the following equation in, okay, basic solution using the lowest possible integer and give the coefficient of H2O. Okay. Questions, we want to know the coefficients of H2O. Data that you have is CrO4 2 minus plus Cu plus Cr, becoming Cr OH3 plus Cu OH2. Okay, so this is actually a question that you have, right? So first step to assign your oxidation number. Okay, oxygen is -2. You have 4 blend, right? That's -8, but the overall charge is -2, which tells us that your chromium will be positive 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 6. Okay. How about us? What is the number of your Cu of copper? 0. Okay. How about here? OH will be -1, right? You have 3 of land, that's -3. But the overall molecule is neutral, which makes your chromium here will be +3. Okay. How about here? OH minus is -1, right? Copper will be +2. All right, so look at this. Who will be your LoRa? LoRa is actually the one that the oxidation number is going to increase, right? So it will be your Cu, right? There will be your LoRa, right? So Cu becoming Cu OH2. Then your GROC will be CrO4 2 minus, becoming CrOH3. Okay, so this is in basic solution, right? Sorry, I forgot to put that in first. Basic solution, if you're missing H, use H2O. If you're missing O, use 2OH minus. Okay. All right, so once we identify our LoRa and GROC, then you start to look at this. Your LoRa, right? On the left-hand side, you have Cu. On the right-hand side, you have CuOH2 in basic solution. Right. So I say in basic solution, okay, anything that actually, if less OH shows up inside your equation, right? Pretend it doesn't exist first, right? So I see you on the left and then pretend that okay, see you on the right. It's already balanced, right? So now you know, okay, it's basic balance, okay? Then you have to put your OH minus back, okay? How many OH minus you have on the right? You have 2 OH minus, right? So all the things you need to do is actually just put the 2 OH minus back and you have everything balanced. Okay? So let's actually how you balance your LoRa. Okay? Then we look at GROC. Okay, you have CrO4 2 minus becomes CrOH3. Okay. So like I say, if you have OH showing up inside your compound, inside your molecule, pretend it doesn't exist first. Okay. Then compare the species. Species on the left is CrO4. Okay, Cr is actually balanced already, right? But right now you have 4 oxygen on the left. That means you need to have 8 OH minus on the right. Okay. Then you come back here and you check it. I already have 3 that already go with my CR, right? That meaning I need to add in 5 more so that I have a total AOH on the right. Okay, so this is your part that you need to make the right decision. Okay, otherwise you found this endless process, just go back and forth. Okay, so once you plug in, then you check. You have here, you have 3 oxygen. Here you have 5 oxygen, totally 8 oxygen, right? And then totally 8 H. Okay. Since you have 8 H, right? So you add in 4 H2O, then you actually balance everything. 8 H, 8 O on both sides. Okay. That's how you balance your zero. Anybody follow this? This is actually one of the trickier questions in this chapter. Okay. So I hope you get it. If you don't, then go back and watch the videos. Okay. Do it slowly. Or you want me to actually redo this again so everybody can follow along? Okay, this is actually how you start with. Okay. For your Jira. Okay. So remember I say in the basic solution, if you see a compound contain OH minus, that's what I mean, this guy, right? You have a CrOH3, right? So in this case, pretend that OH3 minus is not there yet. Okay. Then you will go to see on the left, you have CrO4, 2 minus. This guy, right? On the right, you actually have Cr at this moment. Okay, so you know your Cr is balanced. But on the left, you have 4 oxygen, right? You have these 4 oxygens, right? And then in the basic solution, you have 4 extra oxygen on the left. Then you want to put 8 OH minus on the right. And when we're looking back to the molecule we have here, it already contains 3 OH. Let me actually let's find missing OH on the right. That's why I put 5 OH minus here. Okay, so this is the most critical step with this question. Okay, so once you can do this, once you write out the 5 OH minus, then you'll realize that you introduce, after you balance the oxygen, right, you start looking for your hydrogen. You have 3 H from here and 5 H from here. So totally you have 8 H on the right hand side. To balance that, then use H2O, right? Since each H2O contribute 2 H. Therefore, you need 4 H2O. Balance your H. Okay. And once you finish all this step, then you'll realize everything will be balanced. Okay, including your hydrogen and including your oxygen. Okay, so this is a very key step that you need to be familiar with. Okay, because in your quiz or in your homework, you're going to see a question like this, which is very confusing. Okay, but if you can actually just follow the step that I say, it's actually very simple. All right. So up to this point, we actually balance all the atoms already. Next is actually to balance the charge using electrons. Okay, so here you have 0 to -2. On the right here is 0, right? Therefore, you know you need to add in 2 electrons. to balance your LoRa. Okay, and then for your G-Rock, this is strength -2, 0, 0, -5. Therefore, you can in 3 electrons to balance your G-Rock. Okay. After you balance your LoRa and G-Rock, the next thing is actually you want to combine the two, right? But the electron as produced by your LoRa is not the same as the electron that was received by your G-Rock. Okay, therefore, you actually multiply the LoRa by 3 times. So what we need to do is actually you need to 3 times of your LoRa plus 2 times of your G-Rock. So that the electron that produced by your LoRa will be the same as the electron received by your G-Rock. Okay? So once you do that, you're going to have 3 Cu plus 6 OH minus becoming 3 CuOH2 plus 6 electrons. For your G-Rock, it will become 6 electrons plus 2 CrO4 minus plus 8 H2O becoming 2 CrOH3 plus 10 OH minus. Okay, so all we need to do is actually adding up. 6 electrons will cancel out. 6 OH minus will cancel out with this 10, right? So it's 4 remain. Therefore, your N equation will be 3 copper plus 2 CrO4 minus plus 8 H2O. They give you 3 CuOH2 plus 2 CrOH3 plus 4 OH minus. Okay. And then the question is actually asking for the coefficient of your H2O. Therefore, the answer will be 8. Okay, so let's actually how you solve a question like this. Okay, every time you see the compound contains OH, okay, in your basic solution, then this is actually a very standard way to solve that kind of question. Okay. Is that clear? You good? Okay, so do a few more practice, then that's the difficult one. Okay, I hope you can understand this. All right, so then we can actually enter in the very last topic of this chapter 17, part 1. Okay, so we're going to talk about this electrochemical cell, carbonic cell, or vortex cell. Yeah, vortex. Okay, so that's actually a more common name that you heard all the time in your daily life. It's just the battery. Okay, so what the battery do is actually inside the batteries, there are the chemicals. Okay, so we store the energies in these chemicals. But once they actually connect with some wires, okay, forming a loop, then these chemicals will undergo the redox reaction. Okay, those redox reactions will produce the electrons coming from your battery. They can use it for other purposes of you have. Okay, so what we need to do is actually to understand what's the secret within your battery. Okay, so how these things actually happen using chemical compounds to achieve the goal. Okay, so first thing first, we need to actually first understand the term called the chemical potential of the cell, electrochemical cell, or galvanic cell, or vortex cell. Okay, so we call this as the chemical potential. Okay, so sometimes you're going to see people doesn't call chemical potential, they just call potential. okay, of your galvanic cell or voltaic cell. That's the same thing. Okay. Notation-wise, we use this term E cell, okay, with the cell subscript. E is like a standard form that every time I want to use the potential. Okay. And we use the letter E. So for the galvanic cell and voltaic cell, one very important character is that the chemical potential of the cell has to be positive. Okay. Meaning that it can produce electrons spontaneously. Okay, so if you hook it up to your electronics, then it can provide the power to your electronics. Okay, so every time you see this keyword galvanic cell, voltaic cell, okay, mathematically, implication is that your E cell must be positive. Okay, so that's actually point number one that we need to actually know. Number two, we also need to know the chemical potential is an intensive property. Okay, meaning that this time we realize that okay, for every single chemical cells inside there, you are always going to have your LoRa and Gira, right? So you're going to have the chemical equation go with it. Okay, but all this oxidation and reduction process, you have a specific potential for it. Okay, for example, you have the reduction potential, you have the oxidation potential. Okay, one for your Gira, one for your LoRa. Okay. If you multiply coefficient to a chemical equation, it doesn't change the value of your reduction potential or oxidation potential. Okay, so that's why we call this potential as the intensive property. Okay, that's actually another called the extensive property, which we have learned in the previous chapter. When we calculate our delta G, delta H, and delta S, if you multiply coefficient, okay, of the chemical reactions, your delta G, delta H, and delta S, that value will be changed accordingly. Okay, so we call delta G, delta H, delta S as extensive property. Okay, and for the chemical potential, it's just totally different game. Okay, so don't mess these two things up because I don't know how many times I see this, maybe 1,000 times, but every time we ask you still a very simple question. Okay, A becoming A plus electron. You have oxidation potential. Oxidation potential. Is there a value of 1 volt? Okay, then I ask the student, if I double the equation, what is actually the potential of that? Yeah, there's actually a lot of students will say that it becomes 2 volts. Okay, but that's not correct because potential itself is an intensive property. Okay, so no matter what you do with your equations, that will give you the same potential. So it's very important in to see this. Okay. All right, so that's actually the second point that we need to know. Third point, it's more about calculations, right? How do you have to calculate the potential of your cells? Okay, so it's very simple because we know in all these chemical cells, there are always two processes involved. One is oxidation, one is reduction. Okay, each of them, they will actually have their own values, their own potentials. Okay, so what you do is actually add up the two half reactions to get the overall cell potential. Okay, but the challenging part here is that many people doesn't have a good understanding what is oxidation potential, what is reduction potential. Okay, so that's the things that we're going to practice a lot today, so that we know how to write these things. Okay, for example, they say I have a species A. Okay, and then okay, I want to focus on this species, this reactions. Now tell me the E, not again standard condition. Okay, for that potential, is that the oxidation potential or reduction potential? Oxidation potential. Okay, because let's say the path reaction give out electrons, right? Itself, if you look at the oxidation number of A, it goes from 0 to +1, right? So itself actually undergo oxidation, right? So this is actually the oxidation potential. Okay, so every time we say the potential of the certain species is always referring to the things on the reactant side. Okay, so now I want to actually look at this one. Okay, now tell me what did I do? That's actually reduce reaction, right? Yeah, and then compared to the first example, what is the things I have just done here? I flip the reaction, right? So this one apparently is a reduction potential. Okay, but reduction potential of who? It's okay. The reduction potential of who? A plus. Okay, so every time when we see the oxidation potential, reduction potential, it will always be the species on the left. Okay, so in this case, it will be the reduction potential of A plus. Okay, so the other thing that we need to know is that when we write out these notations, okay, the default, okay, is reduction potential. Okay, you will never actually find the oxidation potential in your textbook because that is not a convention. Okay, scientists always report the reduction potential. Okay, so typically you're not going to see E0 reduce. Okay, you only see this. Every time you see the E naught, okay, it means the reduction potential. Okay, and then, but because the way I teach it to actually differentiate is oxidation and reduction more clearly, right? So you're going to openly see I write is E not ox. Okay, that's just actually the way I want you to see this more clearly. Okay, that's actually the oxidation potential. Okay, so now the other thing I want to point out is that how is this two related if we actually flip the reaction? Okay, so here is actually things you should be very careful for the redox reaction. Okay, potential itself can either be positive or negative. Okay, so sign matters a lot for this chapter. Okay, if you're missing the sign, they consider as a conceptual error. Okay, for this chapter. Okay, so make sure you know the sign. Okay, if you flip the reactions, amplitude-wise, they will be the same. Okay, but sign-wise, it will be just the opposite. Okay, meaning that this will always be true. Okay, so you actually know if you flip things, then you are going to change your potential. Okay, you not only change your reduction potential to your oxidation potential, you also change the species you are looking at. Okay, so it's very, very important you see this. Okay, so that when you use your table, you know what you're actually doing. All right. And then let's say I'm going to use this one. Okay, so you have two half reaction. Okay, I'm going to form a galvanic cell now. Okay. So I have two species. One is undergo oxidation reaction, right? Meaning that is your LoRa, right? A is undergo oxidation reaction, it gives out electrons, right? Oxidation number increase from 0 to +1. So the top half reaction is actually your LoRa, right? Bottom one is a G-rock, right? Because B right now receiving an electron and become B plus. Okay, and then it's going to have its reduction potential, right? So when you actually form a galvanic cell, what you're going to get is actually A plus B becoming A plus B minus. Right, that will be actually the overall galvanic cell reaction you're going to have. Okay, you just end up the two half reactions. So once you have this, then you can actually write out your E cell, which simply equals the sum of the two. Okay, so let's actually how you calculate your E cell. Okay, is that clear? All right. So let's actually the really fundamental way when you calculate your E cell. Okay, first. Provide information of your inner oxidation. G-rock will provide information of your inner, the reduction potential. When you add up the two, it gives you the cell potential. Okay, so here is actually more important that you know the concept because calculation will be actually very simple. Okay, but if you don't have correct concept, then things will mess up quite badly. Okay, so the things we say is right here. Okay, so we're going to do all those examples simply because I want to say this word. Your E cell will be the potential from your anode and cathode. Okay, where your anode will give you the E oxidation, your cathode will give you the E non-reduction. Okay, and all the things you do is actually just adding up. Okay, the other things that we need to say is that one thing you're going to ask a lot in this chapter is actually if I give you a chemical, okay, and I give you the reduction potential or oxidation potential, okay, I will ask you who is actually a stronger oxidant, who is actually a stronger reductant, okay? So those are the things you will be asked, okay? And idea is actually also very simple. Let's go back to here. Let's start from this. Okay, so here actually it tells you the reduction potential of E. Okay, reduction potential of E, right? If that value is bigger, meaning more positive, amplitude-wise larger. Okay, that means the B really like electrons. Okay, so the larger the reduction potential, the stronger oxidant it will be. Right. So this is G-rock, right? So just in case that you forgot. So G-rock stands for what? G stands for gain electrons, right? By itself is reduced, right? It is a oxidant, right? You see the power of my G-rock. So let's actually put every single concept together. Okay. Here, the reason I put it there is because that reminds me if I have a larger Q0, okay, the larger reduction potential. Okay. Then that species will be a stronger oxidant. Okay. So that's the things that we wanted to do. Okay. Similarly, let's look at A. Okay. So A itself like to give out electrons, right? So you have the associated potential called the oxidation potential. Okay, so it's the same concept. It's for LoRa, right? LoRa is what? Lost electron, right? Itself undergo a oxidation reaction, right? Serve as a strong reductant. Okay, so the larger the oxidation potential, it will become a stronger reductant. Okay, so that's what it is. Okay, go back to this. The larger the reduction potential, it will be a strong oxidant, right? Larger the oxidation potential, you will be a strong reductant. Okay, so you can ignore this for now, I think. All right. So let's actually the things that we need to know. The next things we need to know is the cell notation. Okay. But before we actually go into cell notation, we actually know the structure of this galvanic cell and the electron, how the electron is flowing. Okay. So one of the most famous battery that we have is using this very simple equations. Okay. So what this means, we'll get to that point, okay? But chemical equation wise, for your LoRa is zinc become zinc 2 plus. For your G-rock is copper 2 plus, become copper, okay? So you can easily see that how the electrons should be actually put in to complete this type of reaction. Okay, so that's actually the most commonly battery we have in the old times. Okay, so zinc becomes zinc 2 plus, produce 2 electrons, and that 2 electrons eventually give to copper, so the copper 2 plus become copper solid. Okay, so let's actually have two half reaction that's going to happen. Okay, So in the old time, the first generation of battery look like this. You guys did this experiment yet? Already? Okay, so that is actually the basic structure of electrochemical cell, which you need to memorize. Okay, you actually know how to draw these things. Okay, everything that is associated with these pictures, you need to know. Okay. So here, what I do is actually I put in the copper, zinc 2 plus, and copper 2 plus solution. And inside here, you put in a lot of electrolyte. And then at the bottom of this U-shaped tube, okay, you put in some permeable substance that allow the fluid and the molecule to go through. Okay. So typically, here you're going to have a zinc solid plate, and this one will be the copper solid plate. Okay. And then you connect these two plates with an electrical wire and a voltmeter overlay. Okay, so let's actually the basic structure of the electrochemical cell. Okay. So now, what's going to happen is that these two processes will happen spontaneously. Okay. Meaning that if you actually calculate your unstable potential, reduction potential of these two half reactions when you're adding up, they give you a positive value. Okay. So every time when you go and buy a battery, right, you actually specify how many volts of the battery, right? That volt is actually a unit of the potential. Okay, so for these two, you actually have two half reactions. Okay, so for on the things on the left-hand side, okay, this is actually your anode. Okay, because under here, what's going to happen is actually your zinc will become zinc 2 plus and produce 2 electrons. Okay, so your zinc 2 plus will actually goes into your solution. Okay, so where would the electron go? It goes through the electric wires. Okay, and then go to your voltmeter so you know how many volts this reaction will actually produce. Okay, of course, this just half the reaction, right? In order to actually form these things, everything has to form a loop. Okay. So on the right hand side, you have copper. And then inside the solution, you have a bunch of copper 2 plus Ki ions, right? So the electrons will actually go through the electron wire and reach to your copper plate. So right now your copper plate will actually fill with a lot of electrons, right? And those electrons will be received by the copper 2 plus inside the solution. Therefore, you will be deposited onto the plate. Okay, so as time goes by, what's going to happen is that the zinc plate is going to become thinner and thinner. And your copper plate will become bigger and bigger. Okay, so the reaction just continue to go until you consume all the molecules you have in this system. Okay, so a few notations. You know your zinc is undergo your LoRa, right? Lost electron itself undergo a oxidation reaction. It can transfer the reductant, but the very last letter, A, is for anode. Okay, so your LoRa will always happen at the anode. Okay, and they always carry this negative sign. Okay. So for your G rock, okay, N electrons serve as an oxidant, right? And this thing will always happen at the cathode. Okay, that's what the C means. Therefore, this will be your cathode, and it will always carry the positive sign. Okay. So one thing that's actually very important for us to form the loop is this thing is called the salt bridge. So inside here, just a bunch of typically sodium chloride or potassium chloride, ionic species that doesn't involve your oxidation reduction reactions, but it can allow the balance of the charge. Okay, so let's illustrate the first generation of electrochemical cell. Okay, so you have to know the structures, you need to know which side is actually your anode, which side is actually your cathode, right? The way to actually make the judgment is that you need to know who's undergo LoRa, who is undergo G-rock, right? The things undergo LoRa will be your anode, undergo G-rock will be your cathode. You also need to know the electron will flow from the anode to the voltmeter to your cathode. Okay, so those are the key information that you will need to know. Okay. So once we know that, then we can come back to this again. Cell notations. Okay. So the cell notation actually follow a very simple ABC structure. Okay. What's for A? A is actually for the reactions that happen in your anode. B will be your storage. C will be for your cathode. Okay, so it's very simple, right? ABC structure, right? So using the chemical reaction we just talked about here, what you do is actually write out the species that undergo oxidation reaction, which is the zinc. It becomes zinc 2 plus, right? So one thing that you need to be careful here is that the zinc here is zinc solid, right? The zinc 2 plus is in the aqueous solution. They're in different phases, right? So to make that clear, what we do is actually we put a straight line between the two to indicate they are in different phases. Okay. After you finish your anode, then you write out these two straight lines to represent your slope bridge. Okay. And then you write out the half reactions for your C, which is for your cathode. In this case, it will be your copper 2 plus becoming copper. Okay. So make sure you see that I write copper 2 plus becoming copper, right? As a reduction reaction. You can write copper become copper 2 plus. Okay. The order matters. Okay, so it's very important you see this. Okay. So that would be actually the cell notation for the electron cell or galvanic cell we just talked about. All right. But let's actually situation. What if today the reaction will go okay, by itself not serve as an electron? Okay. Here the electron is actually copper and zinc, right? They are solid, therefore they can actually serve an electron directly. Yeah. But actually certain times the half reactions, the substance itself is not solid, it could be liquid. Okay, meaning that it cannot by itself serve as an electron. Okay. So under the case, we will use platinum or carbon to serve the electron. Okay, so if that is the case, then what you do is actually write out platinum, that's your electron. Okay, put a straight line, then you put in your half reactive overlay. Okay, for example, Br minus become Br2. Okay, so bromine itself is always in the liquid form. Okay, so under that case, the bromine cannot serve the electron by itself. Therefore, in the PT, or in the C, the carbon will serve the electron. Okay, then everything else will be the same. Put in your Sawbridge side and write out your G-rock on the other side. Okay, so that's actually how you write out the cell notation. Okay, so with that, that's all you need to know for the electrochemical cell. Okay, any questions? Okay, if not, then let's go through a few examples. Okay, so let's start from this. Identify the oxidizing reagent and the reducing agent in this reaction. Okay, so this is equivalent to the oxidant. This is basically the same as your reductant, right? So basically it's actually, okay, I give you a chemical reaction. Tell me who is actually your oxidant, who is actually your reductant, right? So again, this is a very simple question, right? All you need to do is actually write out your LoRa, write out your G-rock, right? Your LoRa will tell you the reductant. G-rock will tell you the oxidant. Okay. So Q, we want to know who is actually your oxidant, who is your reductant. And you have this O3 minus plus 4 zinc plus 7 OH minus plus 6 H2O, 4 zinc, OH 4, 2 minus plus NH3. Okay, so that's actually a very long chemical equation. Okay, then we start to actually assign the oxidation number, right? So here, O is -2, you have 3 of length, that's -6. But overall, you have -1 charge. That means the N here will be +5. Oxidation number of zinc, 0. O -2, H +1. I mean, this is the same. Here, zinc OH4, 2 minus. OH is actually -1, right? You have 4 of length. So this is actually -1. You have 4 of length, that's -4. But overall is 2 minus. Therefore, your zinc will be 2 plus. NH3, right? H is +1. You have 3 of length. That's +3. But overall is neutral. Therefore, your N is -3. Okay, so let's actually the assignment of your oxidation number, right? And after this, then who is actually your LoRa? Who is your LoRa? whose oxidation number increase? Zinc, right? So you know it's zinc become ZnOH4. That's your LoRa, right? Who's your GRA? NO3 minus become NH3, right? So now it asks you who is actually your reductant, who is your oxidant, right? Reductant, oxidant will be your zinc. Reductant will be your zinc. Your oxidant will be your NO3 minus. Okay? So again, we're repeating the same thing over and over again, right? Know your LoRa, know your GRA. You pretty much solve everything. Okay, so let's actually how you solve these questions. Number 7. Number 8. Determine the E cell for the following reaction using the given standard reduction potential. You have nickel 2 plus plus titanium become nickel solid plus titanium 2 plus. You have your reduction potential of the titanium 2 plus and then nickel 2 plus. And it says assuming X is titanium and what are the YZST? Okay, and how the electron is going to flow. Okay, a lot of questions, right? But let's start one first. The first thing is okay. Basically, calculate your E cell. Nickel 2 plus titanium solid becoming titanium 2 plus. Okay, and then it says the reduction potential of your Ti2 plus is negative 1.63. Reduction potential of your Ni2 plus equals to negative 0.23. Unit is all volt. Okay. So again, who is your LoRa? Titanium. G-Rock will be your nickel, right? And then from the charge, you know that this will be actually a 2-electron transfer process. Okay? So everybody fine with this? Okay, next things I want to ask you is, what's the potential of this? For the LoRa, what is the potential? Are you going to looking for the oxidation potential or reduction potential? For the LoRa, you're actually looking for the oxidation potential or reduction potential. Oxidation, right? Okay, and then for your G-Rock, it has to be your reduction potential, right? So how do you actually get the oxidation potential? It will be the oxidation potential of who? Titanium, right? Right. You need to have the oxidation potential of your titanium. Okay, but do you have that? You have the reduction potential of titanium 2 plus, right? So this means the oxidation potential of your titanium will be negative of that, right? Therefore, you know this will equals to negative 1.63, which equals to positive 1.63 volt. It's very important that you see this. Okay. For your G-rock itself is already a reduction reaction, right? So all you're looking for is actually the reduction potential of your Na2 plus, which is actually written here. This will be negative 0.23. Therefore, the overall, the E cell is going to equals to 1.63 minus 0.23 equals to 1.4 volt. That's how you calculate the cell potential. It's a very straightforward, okay. But the sign matters a lot. Okay, so if you actually mess up with the sign, you're not going to get any credit for it. All right, so that's actually how you solve the E cell, right? But next thing is actually how you're going to label all the things. It tells you the X is titanium. Okay, so if you look at this, titanium is what? Titanium involved in your LoRa, right? That means the X has to be anode, right? It means actually the other side, the T has to be cathode, right? Meaning this has to be a nickel. And inside here, your S has to be a nickel 2 plus. Y has to be a Ti2 plus. The Z apparently is your soul bridge. Okay, an electron will flow from your anode to your cathode. Okay, so those are the things that you need to know for these specific questions. All right, so let's actually help you solve question number 8. Number 9. Consider the following half reaction. Which of the species is the strongest reducing agent? Okay. Strongest reducing agent. Okay, so remember we say reducing agent show up where? In my LoRa, right? Those electrons still undergo oxidation. They serve a strong reductant and always have an anode, right? So you're actually looking for species involved in your LoRa. Okay, means that reaction has to be oxidation reaction itself, right? And then whoever has the largest oxidation potential, that species will be the strongest reducing agent. Okay? So this tells you you need LoRa. Okay? Let me give you 3 equations, right? So if you look at this equation, are they the oxidation reaction or reduction reaction? You have 3 reactions here, right? Are they oxidation reaction or reduction reaction? Reduction, right? But that's not what you're looking for, right? All you need is what? The oxidation reactions, right? So how do you get oxidation reaction from here? You flip it. Okay, so that's the thing that you will need to do. Okay, Q is actually find the strongest reductance, right? So data is actually, you want to actually start from the LoRa, right? Therefore, you flip it, become AU solid, become AU plus electron. Then your E naught oxidation will equals to negative 1.69 volt. Okay, second one will be N2 plus H2O. They give you N2O plus 2H plus 2 electron. Your E naught oxidation will equal to negative 1.77 volt. Third one will be Cr solid becoming Cr3 plus 3 electron. Your oxidation potential is going to equals to positive 0.74 volt. Okay, so that's your LoRa, right? Once you have all this oxidation potential, you want to looking for the equations with largest oxidation potential, right? So in this case, the third one gives you the greatest oxidation potential, positive 0.74, right? Therefore, the species will be the strongest reductant. So the answer will be your Cr solid. Okay. So it's very important that when you read the questions, right, you're going to know what kind of equation that you need to use and what kind of potential you want to do. Right. Here, because it says strongest reductant, therefore you know you go with your LoRa. Therefore you know you flip the reaction to calculate your E naught oxidation. Right. And you can even identify the equation as the largest oxidation potential. Right. However, species presents on the left, then they will be actually the strongest reductant. Okay, is that clear? Any questions? If not, then I will ask you a follow-up question. Among the three equations, which species is the strongest oxidant? Okay, so the logic flow will be, since I'm asking for the strongest oxidant, I will need to use my G-rock, right? Then actually I'm going to looking for the reduction potential. Okay, so which one give you the largest reduction potential? The second one, right? So you have N2O and then H plus. So that N2O will be the strongest reductant. All right. So if you follow the proper logic, solving this type of question is actually very easy. Otherwise, it looks like very, very confusing. Okay. And by now, you should see the full power of my LoRa and G-rock, right? So I'm actually use that. Okay. Again, my own invention. If anyone claims they invent this, that is a lie. Okay, I've been doing this for many years now. Okay, and I found this actually the easiest way that you can understand the topic. Okay, yeah, that's it for today. Thank you.